Dear student, welcome to my channel. Topic of this video is support vector machine. This is the second video on this topic, and in this video I am going to explain SVM for simple two-dimensional example. SVM is mapped as a constant optimization problem. Objective of SVM aims to find hyperplane, that is nothing but decision boundary, that maximally separates two classes of data points in high dimensional space. Margin is the distance between the hyperplane and closest data points from the class, that is nothing but support vectors. The goal is to maximize this margin. Now here we are dealing with the hard margin SVM, that is in which data is clearly linearly separable. SVM is a constant optimization problem in which our objective function is to minimize this 1 by 2. W is nothing but the weight vector, that is norm of the weight vector square, and constant is all points should be classified correctly. So this is the quadratic optimization problem of SVM. So our objective is to minimize this, and subjective to constant that all our points should be classified correctly. Now we will see the simple example. 6 points are given, 3 points belongs to class A and remaining 3 points belongs to class B. We tried the Python programming on this data set, solving the optimization problem by solving the quadratic programming problem using Python. The decision boundary that maximizes the margin is found. The optimal decision boundary turns out to be line x plus y minus 8 equal to 0. Now first we will see the points in visualized manner. So these are the 3 points belong to one class, these are the 3 points belong to one class. Now for this class, this can be support vector, for this class this can be support vector, and for this class these 2 points are the candidates for the support vector. So when we did Python programming at that time, it take only this as a support vector for this class and this point as a support vector for this class, and in between this the boundary is mapped. Now see this output of the Python programming. So this is the one class support vector, for another class support vector. Now from this support vector we draw this line, this area is nothing but margin. Our aim is to find out the maximum margin. Then this is the decision boundary, and the W vector is perpendicular to this decision boundary. So this orange is a W vector, that is a weight vector, which is perpendicular to decision boundary. Now the same output but in a different window. Support vectors, and they form the margin, and this is the decision boundary, and this W vector is perpendicular to this decision boundary. Now through programming we got the W vector as minus 0.33 and minus 0.33, bias as 2.67, and from that we can easily calculate the margin, that is 4.24. The equation of the decision boundary is W x plus B equal to 0. Now here we are getting W as minus 0.33 and minus 0.33 and B as 2.67. So if we write down this equation, or here we can write down, instead of x5 we can write down x1 x2, it's all depend on how we represented the column name. So this is the two-dimensional data. So when we divide by minus 0.33, we are getting this form x plus y minus 8.09 equal to 0. For simplicity we will just keep minus 8, so x plus y equal to 0. So the points 08, 80, 45 line on this line, because the line equation is x plus y is equal to 8. Now this is the weight vector W, this is the bias. Here we find out the norm of the vector, which is nothing but square root of W1 square plus W2 square, so which is equal to 0.47. So our aim is to minimize this particular constant. So our aim is to minimize this 1 by 2 norm of W square, which is equal to 0.11. So we want to minimize this value, because when we minimize this value our margin get maximized, because the margin is 2 divided by norm of W vector. So 2 divided by 0.47 is equal to 4.26. So we are getting the we are getting the margin between the two classes as 4.26. Now here we check that we can find out the distance from every point we can find out the distance from decision boundary to every point, and the formula is like this, that is distance is equal to ax0 plus cy0 plus b, where x0 and y0 they are nothing but our points, and a and c are nothing but the components of weight vector, that is nothing but minus 0.3 minus 0.3. This b is a bias and divided by that norm of the vector. Now we will see for our example. So these points are there, and here I added these points because the line equation is x plus y equal to 8. So 0 plus 8, 8, 0, 4, 4, they will lie on the decision boundary. So when we calculate the distance from the decision boundary by using this formula, so we are getting the distance like this. So we are getting the distance like this, and for decision boundary we can see that all the distance are close to all distance are 0. So here we can see that 0, 0, 0, because these points lie on the decision boundary. Now here we can see that for the blue class, so these two can be candidate for the support vector and they lie on this particular margin, so therefore their distance is 2.17, and we can see that total distance is 4.24, so half is 2.17. and for the another class, this point only acts as support vector, and therefore the distance is 2.04, and you can see that the half of the 4.24 is close to 2.04, and remaining points are away from that margin, so therefore the distance is 3.45, 3.45. So in this way we can make, so these are the class 1 and these are the class 2, and when we put the value in the equation, that is y w to x plus b, so for this we are getting, if we keep this class as positive, then we will get the positive answer, and if we keep this class as negative, for this we will get the negative answer. Now why to maximize the margin? Because when we maximize the margin, at that time the chances of error during for the test data will minimized. That's why we will keep maximum or maximize the margin. So here just example is given. For example, we want to minimize this, so when we minimize this, margin get maximized. So here the norm of the vector is 8421, so I have taken just randomly value 8421. So when the norm of the vector is reduces, at the same time this 1 by 2 w square is 3282.5, that is as this norm of the vector is reduces, since 1 by 2 w square is also reduces, and which will increases the margin. And now here we can see that as this 1 by 2 w square is minimizes, so margin gets increases, so this minimizes and margin get increases. So in this way we require to keep the norm of the vector minimized, so that this term will be minimized and this term will be maximized. So if we put the one class we treat as a +1 and another class we will treat as a -1. So for the we have seen just the distance of all points from the decision boundary, but if we want to classify, we can easily classify with this formula also. Rationale for maximum margin. Decision boundary with large margin tend to have better generalization. If the margin is small, then any slight deviation of sample to be decision boundary can have a quite significant impacts on its classification. Classifier that produces decision boundary with small margins are therefore more susceptible to the model overfitting and tend to generalize poorly on previous unseen sample. Therefore, our aim is to maximize the margin. Thus, during the training or learning phase, the approach would be search for the hyperplane with a maximum margin. Such hyperplane is called maximum margin hyperplane, and it may be abbreviated as MMH. Now we'll see another problem. Now this is the class A and this is the class B. Now here we can see that these two can be candidates for the support vectors, and here these three points can be candidate for the support vector. So this is nothing but the margin formation, this is decision boundary, and the support vector is perpendicular to this decision boundary. So when we implement this program in Python, we are getting the weight vector as -0.25, -0.25, bias as 2.25. Support vectors, it takes only these 2 points as a support vectors, for this class this point and for this class this point, and margin we get the 5.71. so maximum margin is there. And here the equation for the line is minus point, because equation is wx plus b equal to 0 and w is minus 0.25 minus 0.25. so by adjusting the equation we are like getting the line equation x plus y minus 9 equal to 0. so 0.09905445 lie on this decision boundary. And in the next slide, or in the here, the distance are from every point, distance are found from the decision boundary. And here, as for the first class, these 3 points can be candidate for the decision boundary. So for the margin, these 3 can be candidate for the support vectors. So here you can easily check that their distance are getting same, that is 2.86, and the 1 2 is far away from the decision boundary, so distance is 4.91. For second class, 2 points are candidate for the support vector, so they are getting that distance 2.86. so distance is actually positive, so here negative indicates that this belongs to the another class, but distance has to be represented positive. But the same way the classification comes, when the negative value comes, it belongs to the second class, and when the positive value comes, it belongs to the first class. Then this particular 2 points from the class 2, they are the candidates for the support vectors, so their distance is coming 2.86. Margin is 5.71. so from the one class the distance is 2.86, and from the second class also 2.86. so if we add, we will get the close to the 5.71, and the remaining points are far away from the boundary, so we are getting the distance as 4.29. and here 0990 or 5445, we will get the distance as a 0 because they lie on the decision boundary. So this is all about the to understand what is mean by support vectors, what is mean by margin, how we calculate the norm of the vector, how we found the margin, and how we can find out the distance from each points to the decision boundary, and even we can classify the points. So one class we treat as a positive and one class we treat as a negative. Thank you.